Hello everyone. Now we're going to be talking about concavity. So the first derivative of a function tells us if a function is increasing, decreasing, and where there are extrema, maxes or mins. The second derivative of a function tells us the rate of change of the derivative. So in other words, how fast the function is increasing or how fast it's decreasing. And this basically influences the shape of the function, where a graph can be concave up or concave down. And I literally think about these as smiley and frowny faces. So if you look at, these blue functions right here, so this is kind of like a frowny face in this position. So this is concave down. Over here, the concave down part would be there. And concave up, where you have more of a smiley face. Hey, we have a big smile right there. This is concave up. And then in the other spot, this is concave up. Okay? So more precisely, a function is concave up on some interval AB if the graph of the function lies below its tangent line at each point. So look at this concave up here. If I draw a tangent, okay, the function lies above its tangent line. If I draw a tangent here for the concave down, the function lies below. Okay, so if a function is concave down on some interval AB, that's if the graph of the function lies below its tangent at each point in AB. Okay, so if that's confusing to you, just think about smiley face, frowny face. Okay? Now, the point, if we look here, there's a point basically where we switch from a frowny face to a smiley face. That point where that switchover happens, that's called an inflection point or a point of inflection. So this is an inflection point. And so it's basically the point where the graph changes concavity is called an inflection point. This occurs at the value either where the second derivative is 0 or it does not exist. So the point of inflection, as it's sometimes also called, so POI, if we use that, this will be point of inflection, by the way. So in these pictures, roughly this is where the point of inflection is in the first one. And in the second one, that's roughly where the point of inflection is. Okay. So that's the general idea of concavity. Now, just as a function can be increasing or decreasing on an interval, this is also true for concave up and concave down. There can be certain regions where you're concave up or concave down. So if we look at this first one, for example, this is like a smiley face. So in that whole region, this is concave down, concave up, where this first part, our function is decreasing, and then we're increasing. For this function, which is actually always increasing, its concavity is not consistent. So for the first part, it's more like a smiley face, and then we switch to a frowny face. So this part's concave up, this part's concave down. This last example here, this whole thing is concave down, okay? We have a general sort of frowny shape where the first part is decreasing, the other part is increasing. Okay, so sometimes the whole interval has a certain concavity, sometimes it's split up. Now, is there a fast way to tell where f is concave up or concave down? And of course, similar to the increasing decreasing question, yes, we have a test. I feel very theatrical today for some reason. Maybe it's because I'm standing. Anyway, sorry. I've been filming too many of these videos today. So test for concavity. Let's say we have a function. First and second derivative are defined on some interval. So we don't have discontinuities, anything like that. If we have that the second derivative, so f double prime of x is greater than 0 on this interval AB, then f is going to be concave up. Similarly, if the second derivative is less than 0, then we're going to have that it's concave down on that interval. So very similar to increasing, decreasing, the process is exactly the same, except instead of analyzing the first derivative with a critical point, you're analyzing the second derivative point with, the second derivative with a point of inflection. Okay, so let's just jump in and do an example of this. Let's say we have this function. We want to find the points of inflection and where the function is concave up or concave down. So what do we need? We need our second derivative. So let's differentiate for the first time. So by power rule, I'm going to get 4x cubed minus 8 times 3 is 24x squared plus 18 times 2 is 36x. Differentiate again. I have a 12x squared minus 48x plus 36. And now polynomial, so we don't have any issues with discontinuities or points not existing for the function or the first or second derivative. So let's set f double prime equal to 0 and solve for x. So I'm going to have this 12x squared minus 48x plus 36, and I am going to factor out a 12. This will give me x squared minus 4x plus 3. And then you can get rid of the 12 if you want. But again, when you do the check to see if f double prime is positive or negative, you're going to have that 12 in there. This is going to be x minus 3, x minus 1. So either we have x minus 3 is equal to 0, or we have x minus 1 is equal to 0. So this is going to give us x is equal to 3 and x is equal to 1. So our points of inflection, 3f of 3, which if you plug 3 into the function, you're going to get 27. So 327. And the other one, 1, f of 1. If you actually plug 1 into your function, you're going to get 11. So these are the points of inflection. And similar to before, this is going to tell us how to split up our interval to check for concavity. We have a point of inflection at 1, and we have a point of inflection at 3. So we're splitting up our interval into this section, and this section. Just like we did before, except now with the second derivative, we're going to make a chart and we're going to see if the second derivative is positive or negative at some test point in between each interval. Okay, so we have the interval from negative infinity to 1, 1 to 3, 3 to infinity. So for my test points, I can do 0, so I'm definitely going to do that for this one. 2 between 1 and 3 is probably best. And then let's do 10. 10. All right, so what do we have here? So this is negative. Negative, so negative times 12 is positive. This is negative, this is positive. Times 12, that's going to be negative. And then what? This is positive, positive is positive. Times 12, still positive. Okay, so for concavity, because it's greater than 0, this is concave up. This one's concave down. This one is concave up. Okay, so concave up, we're what? Negative infinity to 1 and 3 to infinity. And then the concave down part, that's going to be between 1 to 3. Now, for concave up, again, thinking smiley faces and frowny faces. So we have a smiley face here, frowny face here, and then a smiley face here. And then these are the points of inflection. Okay, so this is concave up, concave down, concave. And just to build some intuition, let's take a look at what the function is. So where are the points of inflection? So the points of inflection, let me get red here. Oops, sorry. 1 and 11, so roughly here. And then the other one was at 327, so roughly here. And yeah, that makes sense. And I'm saying, yeah, that makes sense because we have that, you know, it's kind of a smiley face looking thing right here. And then all of a sudden, I'm switching concavity. My shape is now more downward shape. And then once I get to 327, oh, it's kind of a more smiley face situation. Okay, so this is where our f double prime of x is greater than 0 in the pink parts. And then we have that f double prime is less than x in this blue sort of part. Okay, just to build a bit of intuition. Now, finding the values where f double prime is equal to 0 does not mean that, does not mean that a point of inflection. Oh, does not mean that the x is a point of inflection. Now, what we mean by that is it doesn't mean that we switch from a smiley to a frowny face. An example of this is x minus 1 to the power of 4. If you look at the plot, it looks like a really big bowl, like a really wide bowl at the bottom. So f double prime of x is equal to 0 at x is equal to 1, but I don't ever get that it's concave down and then up or vice versa. I don't get something like this and then it changes like that. I always get that it's a parabolic type shape. Okay, so the other thing concavity can be used for is it can be used to help you find if a critical point produces a relative extrema. It's an alternative to the first derivative test, and it's actually called the second derivative test. And sometimes it's very difficult with the first derivative test, and some people just prefer it. So the second derivative test tells us that if we have some critical point, okay, specifically where f prime of c is equal to 0, and you have the second derivative exists on some interval, except possibly at that critical point, then we have the following. So if I take my critical point, let me zoom in a bit, and sub it into my second derivative, if I get that that's greater than 0, it's the opposite what you would think. F of c is a relative min. And if we plug in c into f double prime and get less than 0, then f of c is a relative max. Now, remember when we were drawing derivative functions and we were trying to figure out peaks and valleys? This can be used for that, to figure out those points. But we'll talk about that more later in the week. Now, if we have that f double prime of c is equal to 0, or it does not exist, this test is inconclusive. You have to resort back to the first derivative test. Okay, so with this little picture here to help build up some intuition. Okay, so these are the spots where our second derivative, is greater than 0. This is the spot at this peak here. F double prime of x is less than 0. Okay, this is the relative max. And this one is the relative min. And that's a rough picture to help you see what it looks like. Now, let's do a quick example of this. And again, unless I ask you to, you don't have to do the second derivative test. You can do the first derivative test. But let's find all extrema for this function here using the second derivative test. First thing I need are the actual derivatives. So by power rule, I'm going to get 12x squared plus 14x minus 10. Differentiate again. I'm going to get 24x plus 14. Okay, this is a polynomial. We don't have any issues with discontinuities. So let's set this equal to 0 and the second derivative, but also the first derivative, because now I also need my critical points. Okay, so my first derivative was the 12x squared plus 14x minus 10. I'm going to factor out a 2. So I'm going to get a 6x squared plus 7x minus 5. If we factor this, you can do it with the quadratic equation if you want to, or if you're good with factoring, you can just state the answer. Okay. Now, this is telling us that either 3x plus 5 is equal to 0, or 2x minus 1 is equal to 0. So our critical points aren't the prettiest in the world. I have a negative 5 over 3, and I have a positive 1/2. And sorry, we don't need the point of inflection, so we don't have to solve f double prime is equal to 0. I'm only caring about the critical points and using the second derivative test right now. If I wanted the points of inflection, then I would have to set f double prime is equal to 0. Okay, so now let's actually try the second derivative test. So my second derivative was this thing, and I have my critical points, so I'm going to plug them in. Okay, so I'm going to start off with the negative 5 over 3. Plug this into here. And when I simplify that, I will end up getting negative 26. This value is less than 0. So my function at negative 5 over 3, if you plug that value into your function, we're going to get this output of 691 divided by 27. And this is a relative maximum. Again, it's the opposite. Because it's negative, it's going to be a max. Similarly, if we put in a half, our critical point half into f double prime, I'm going to end up getting 12 plus 14, so that's positive 26. And if I actually put a half into the function to see where that corresponded to, it would give me 21 over 4, because the second derivative of that critical point is less than 0, or sorry, it's greater than 0. By the second derivative test, this is a relative min. Okay? Alrighty. So hopefully you found that helpful. Thank you very much.